The increase in renewable generation is transforming the conventional design and operation of the electrical grid. In particular, modern distribution grids encounter additional obstacles such as the need for new infrastructure and the connection of electrical vehicles and energy storage systems operating at different voltage levels. To address these challenges, the iPlug project, supported by the European Union, aims to create innovative power electronics utilizing multiport converters. These converters will enable the seamless integration of multiple renewable energy sources, energy storage systems, and loads into the distribution grid. By deploying these converters across different applications, the iPlug project aims to alleviate grid congestion and enhance overall grid performance.
Modern power systems are experiencing a deep transformation because of the high penetration of renewable energy and the challenge of electrical mobility. We are seeing this in distribution networks, both at medium voltage and low voltage level. And basically in this context, it is where the iPlug project is proposing solutions to enhance the integration of these renewables, electrical mobility, and also allow to flow more power in distribution networks. So basically we are looking at designing the systems, studying specific distribution systems and proposing solutions based on multi-port converters.
Well, the main thing is we have distribution grids and we have a lot of renewables that has to come into the distribution grid and how effectively we integrate them. The project in general will develop the converters that will enhance that transition. So we can integrate easily and in abundance these renewables. So that's a way also going towards zero carbon emission strategies. So that's the way we are going.
Multiport converters are expected to improve grid stability and reliability, increase renewable integration, generate cost saving, increase flexibility in the grid operation.
Yeah, we see iPlug as being very beneficial on DSO's network, both at helping integrating solar photovoltaic at residential areas, for example, as in our low voltage use case, being able to optimize the flow between solar PV and EV vehicles in a household area, but also helping our low voltage networks that are very radial become meshed and offering redundancies to be able to optimize the grid network, but also on a medium voltage level or even on our sub-transport to be able to help with the normal and regular operations of the grid.
At the end, some solutions close to multi-port converters have been presented, such as soft open points or solid-state transformers, but the main benefit of multi-port converter is that it's everything on the same device. So by using these multi-port converters, we will reduce a lot the number of components, and this produces a lot of economical benefits compared to the already presented solutions.
The iPlug project is led by a consortium consisting of 5 academic and research partners alongside 3 industrial partners from 5 different European countries. Their collaborative efforts have driven the development of multiport converters, combining exceptional technical expertise with practical real-world applications.
In the project, we have partners bringing different knowledge. On the one side, we have academic partners which are specialized on power systems and power electronics. Different partners are working on different topics related to the technologies. And in addition, we have also partners involving operators and manufacturers which are bringing a specific knowledge and information on the real-world application of the systems we are proposing.
I think the consortium itself is one of the strengths of the project because we have actors from all the ecosystem, basically having universities, so all the research, this technical know-how, plus companies like ours and where we provide experience and this, let's say, this synergy. When we work together, research and companies, we can generate results that have a profound and valuable impact on the real world and on the real system.
CITCEA-UPC is proud to be a partner of the project where we support our university partners and researchers to develop their cutting-edge and microcontrollers with our industry-grade model-based engineering solutions.
This has provided a really unique opportunity for partners to both collaborate on the strategies that they're trying to design and make sure that their individual tests can access real-time applications without too much complicated equipment and challenge.
Effective planning and operation of distribution grids are crucial for ensuring a reliable, efficient, and resilient power supply to end users. Proper planning helps to optimize the grid's capacity, accommodate future demand, and integrate renewable energy sources, while efficient operation ensures minimal downtime, quick response to faults, and cost-effective management. By focusing on both strategic planning and real-time operations, utilities can enhance grid stability, reduce energy losses, and improve overall service quality for consumers. The main contributions of the iPlug project in relation to planning of multiport converters are implementing an optimization-based methodology to size the power of the multiport converters, evaluating techno-economical indicators to compare different multiport converter configurations and locations, analyzing the benefits of multiport converters to improve the resiliency of distribution grids.
We can evaluate the benefits of multiport converters using KPIs, which are divided into categories: network KPIs and converter KPIs. Network KPIs are to evaluate the efficiency, the available capacity, and the renewable energy, and converter KPIs are to compare with conventional solutions, considering aspects as size, design, and cost.
Well, in order to evaluate the benefits of multiport converters at planning stages, we can simulate how it would behave on the different positions where the multiport could be placed. And that will help us not only to see the benefits of the multiport, but also to try to forecast which are the requirements or what do we need it to be able to accomplish.
So to evaluate the benefits of multiport converters at planning stage, we defined two sets of features, critical ones that power converter topologies had to comply with to fulfill an application, and then a second set of desirable features that maybe weren't absolutely critical but made it more useful for that application. Things like the power density, the complexity, the resilience. So we used the critical topologies to qualify and disqualify lots of topologies, and then we compared the qualified topologies in terms of the things that we thought were desirable for the specific applications, and that was a way for us to cover a lot of topologies and focus them in for specific applications.
Well, with in iPlug, we have been looking at several scenarios. We have found that the multiport converters are suitable in a range of applications, including low and medium voltage. For example, we have seen that in low voltage applications, we are able to integrate in a single device, electric vehicles and solar panels and batteries. That is applications that they are more and more popular among low voltage and residential uses. And also what we have found is that multiport converters have several advantages in medium voltage, where, for example, we can connect two feeders at the end of the medium voltage line, like a soft open point, but there we can add other applications, for example, EV chargers for a community car park, but also we can add some solar panels there.
I think multiport converters is a quite powerful concept that can be very, very useful for the electric vehicle charging infrastructure. When you charge electric vehicles, you usually have a lot of converters, but the multiport converters can reduce the conversion stages and charge many vehicles using just one converter, which is quite powerful for efficiency and also for safety reasons.
So we think multiport converters are really useful when you've got a lot of energy resources that require multiple discrete conversion stages to integrate them. If we can co-locate those energy resources and share components, whether it's passive or active components, then we can improve the efficiency and maybe the power density as well.
In iPlug, an A provides use cases to test the technologies that have been developed by our partners. We have 3 different use cases at low voltage, medium voltage, and also in the sub-transport network. The idea is to analyze the impact of the iPlug technologies on a real network.
We have also developed a resilience analysis for distribution grid that we have applied to evaluate the impact of multi-port converters. Actually, nowadays, resiliency for grids, distribution grid is very important, especially for rural areas. So we have clearly evaluated that multi-port converters can highly increase the resiliency and reduce the amount of people that is affected by events like fires or flooding.
The main contributions of the iPlug project in relation to operation of multiport converters are optimal power flow algorithm considering multiport converters in distribution radial grids, identification of instabilities in multiport converters and distribution grids with small signal analysis, system-level control of distribution grids with multiport converters.
We assessed the capability of soft open points based on multiport converters to improve grid reliability by modeling different grids. On one end, we modeled benchmark power grids such as the IEEE 33 bus system, and on the other hand, we modeled real grids, in particular a low voltage grid from ANED, our DSO partner in our project. And after modeling them, we simulated their behavior, solving an optimal power flow problem, in particular optimizing the losses, so minimizing the losses, and minimizing also the voltage deviation as an alternative objective function.
So some of our other contributions for the medium voltage multiport converter was trying to enable it to support the distribution network better. We were interested in doing this using grid forming, converter control strategies. We were aware of some of the complications associated with implementing grid forming control in distribution networks because of the impedance characteristics. So we explored conventional grid formers and some weakly nonlinear grid forming control types. We identified their strengths and weaknesses and tried to explore ways to mitigate those issues.
Multiport converters can be employed as soft open points, and soft open points are the evolution of traditional switches in distribution grids. They have the advantage of enabling power flow control, both active power and reactive power, and this allows improving the reliability of distribution grids. So, for example, we can reduce grid losses thanks to the presence of soft open point. The topology of the distribution grid can be changed, and this can affect, for example, the propagation of faults in the power grid, or the voltage deviation in different nodes of the power grid can be improved thanks to the optimal operation of these soft open points.
But we mainly focused on isolated topologies, so the ones you see in triple active bridges or multi-active bridges for soft open point solutions. We focus only in the small signal stability analysis, and we find out that for speed control parameters affect different capacity, slow, and oscillation flows.
In conclusion, multiport converters will be essential components in the distribution grid, requiring careful sizing and strategic placement. They can also be dispatched as both generation and storage units, offering enhanced flexibility and efficiency in managing power flow across the grid. iPlug. Innovative power electronics solutions for a greener electrical grid.